So my final story has some overlap with Dimitri's story about the extrasolar planets found around the TRAPPIST-1 star. So this is a paper that just came out, and it's titled Prebiotic Chemistry and Atmospheric Warming of Early Earth by an Active Young Sun. And so right away, prebiotic chemistry, that suggests we're dealing with biology, and that in fact is what we are talking about. And it basically has to do with solar flares. So you saw images or video like this from Dimitri's story, but this is from the Solar Dynamic Observatory. And so we're looking at extreme ultraviolet images or movies of the sun's surface. And what we saw was a solar flare kicking off. So let's see if we can repeat this. So right here is where the solar flare, or right there, gets emitted. And the sun just periodically has these ejections of high energy particles along with X-rays. These are just very energetic regions of the sun that blows off material. And the material, if it's aimed directly at the Earth, can impact the Earth's upper atmosphere and cause aurora. For extremely powerful solar flares, they can actually affect electric transmission lines down on the Earth. So scientists, are really interested. Solar scientists are interested in in studying the sun, just because there is a direct impact from what happens with the sun versus what can happen to us here on Earth. But another interesting result that has come from the Kepler spacecraft's observations of planets around other stars, and the Kepler spacecraft uses the same sort of transiting technique that Dimitri was talking about, where it looks for slight dips in the light from the sun or from these other stars. But because it's constantly monitoring, or has been monitoring the same set of stars, it's also able to find flares from the stars that it's looking at. And so one of the surprising or interesting results from Kepler is that for young stars that are still sunlight, but they're much younger than their sun, they tend to have solar flare activity that's much, much higher than our suns. So the most massive solar flare that we know of in at least our recent history with our sun was something called the Carrington event, which occurred in the 19th century. And that was a massive solar flare that basically set fire to like telegraph stations because there was so much current being generated that was being picked up by telegraph lines. And it's much more massive than anything that we've seen in the last 100 years. But those type of events occur maybe once every century from the sun. And of course, when it happens, it has to be aimed right at the Earth for you to be affected. But those events occur as much as 10 times a day for stars that are only 1 billion years old, as opposed to 4 billion years for our sun. And so it's thought that if this type of activity holds for our early sun, then we would have expected the Earth to be impacted by these solar flares, just because they would be so much more frequent. And if we think about what the early Earth was like, it probably was very different atmosphere-wise. There likely was a lot of nitrogen, so molecular nitrogen, which is 2 atoms of nitrogen held together, but there wasn't any oxygen at all. Instead, most of the atmosphere, the remainder of the atmosphere was mostly carbon dioxide, or CO2, and there might have been a trace amount of methane. And this was likely what the Earth's atmosphere was like for the first billion or 2 billion years before life was dominated enough to start pumping oxygen into the atmosphere. So the early Earth's atmosphere didn't have any oxygen. And the nitrogen turns out to be a very inert molecule, meaning it takes a lot of energy to split the two nitrogen atoms. And the early Earth probably didn't have a lot of the precursors, the molecular precursors to life that are important to get life started. And so one of the questions that people who study early life on Earth, astrobiologists, have wondered about is how do you get all those important elements or compounds that are important for to get life going on Earth. Well, it turns out that if you have these powerful solar flares, this is one way to do it. And what happens is these solar flares can actually compress the Earth's magnetic field. So our Earth's magnetic field protects us from the rain of energetic protons and electrons that are coming from the sun. But if you have a flare that's powerful enough, it actually compresses the magnetic field. So this is what the magnetic field normally looks like with the Earth here, and the sun is off to the right. But if the Earth gets hit by one of these powerful solar flares, it basically pushes down on the Earth's magnetic field, and those charged particles from the sun can now rain down onto the Earth's atmosphere. And those particles are now energetic enough to break down the nitrogen. So here is a movie created at NASA Goddard to sort of demonstrate what might happen. So there you just saw the solar flare, and here's the solar flare particles coming, pressing down on the Earth's magnetic field, and that allows those charged particles to now get down into the Earth's atmosphere. And because the Earth's magnetic field was naturally weaker in the past, what also happened is that not only are you getting aurora, but you're getting aurora at much more southerly latitudes than you'd find today. So today, you normally find aurora in northern Canada and in Alaska, but here you'd probably be seeing aurora like in South Carolina, or definitely south of us in Colorado. The authors of this paper also worked on what would happen chemistry-wise. And so they figured out that the nitrogen molecules could be converted to a number of different species. And so it includes, let's see, this is ammonia, HNO, NO, HCN. These are actually molecules that are important for the precursors to biology as we know it today. So this is actually one way that you can populate the Earth's oceans with molecules that could eventually form RNA and DNA. And then the other thing that's really interesting is that a lot of nitrogen or nitrous oxide, what we think of as laughing gas, also gets formed. And nitrous oxide is important because it's also a very powerful greenhouse gas. It can actually, it's about 300 times stronger as a greenhouse gas than carbon dioxide. And the reason why that's important is something called the faint sun paradox. And this is kind of a confusing plot, but the present day is over here, so that's where we are. And 4.5 billion years ago, when the sun first formed, is at this end. And this line here shows the solar luminosity. So based on our stellar models, or models of how stars form and evolve over time, we think that the early sun was actually about 70% the brightness or the luminosity of the sun today. And this is a problem because if the Earth was exactly the same in the past as today, we would find that the Earth's temperature is this black line here. It would basically, we would find the Earth completely frozen at about the 2 billion, 1.8 billion year mark, just because the heat that we're getting from the sun is much less in the past than what we find today. And this is a problem because if we look at the geological record, we actually find evidence of life starting at about 3.5 billion years. And there's also a lot of evidence that the Earth had liquid water, that there were oceans. And so there's no evidence for the Earth to be completely frozen for billions of years at a time early on. And so the question is, and this is a problem that people have been working on for 30 years now, how was the Earth able to stay warm and for the oceans to be liquid even when the sun was much less luminous in the past? And this particular work with the solar flares might be one possible answer. So not only is it providing an answer for creating the ingredients for life early in the Earth's history, but it's also providing a way with nitrous oxide to keep the Earth warm via this extremely strong greenhouse gas.